But we just wanted to show some really brief demos to basically start you thinking. There's a whole suite of probes that you can buy. There are some other ones that, maybe some crucial ones that you might want to buy. It's just to start to think, just in case you haven't already. We've been doing all these digital, like on the computer technologies, but for science and for math, there are some really nice hands-on technologies that can really augment inquiry. So with that, I will turn it over to Yash for the first demo.
Okay. Well, before I get started with this, I just want to. Here's a problem that I had before I used Prober in my classroom. Okay, and you can put yourself in this situation. Let's say you're in a chemistry or physics lab as a student, and your teacher gives you a lecture, and they're like, okay, go to this lab, and you do the lab, you do all the calculations, and you look at your bird, and you say, what was the point of all that? Right? And that happens all the time.
Yep.
Happens all the time. And before I started using Prober in inquiry-based lessons, my students would come to me and say, Patel, what was the point of this again? Oh my God, nothing makes you want to bang against the wall more than that question. So then I started using Prober and inquiry-based learning, and basically the approach is you do the lab and you fill in the gaps with lecture information. And probes really help you in doing that, and it gives students a reason for doing what they did. And it gives them immediate feedback and a reason for doing what they did. Like, why did we do this well? We're filling the gaps now, as opposed to waiting a day and doing lab day. So these are really basic things I want to show you. For instance, this is a GoTemp, and so this does not connect to a LabQuest or anything like that. You just plug into your computer, and as long as you have Logger Pro Lite or just Logger Pro, it should record the data.
And Logger Lite is free. You can download it. It's a free software. And like I said, it's just up into the USB port.
Yeah, and so let's just do something really simple. For example, the temperature of this room right now is 22.7 degrees Celsius. I want to make sure my probe's working, so I'm just going to keep it up a little bit and make sure it's working. So yeah, so you see the temperature increasing at 24, 24.4. And so I'm just making sure that works. So, for example, if I put this in cold water, which I have right here, it's going to go to its minimum, which probably close to 4 degrees. And let's say that you want to figure out what the rate of heating is at room temperature. Okay? So a way to do this is just let the water sit, and over time it'll collect enough data to show you some kind of curve for at what rate the water heated up back to room temperature. But obviously we don't have that kind of time, so I have hot water here just to show you.
Okay, keep going.
Yeah. And so I guess it's pretty steady at 2 degrees Celsius. And so if I add hot water to it, maybe it's on hot, you can see that the water's going to warm up again. And this software enables me to take the slope of that, or I can do a lot of functions with it, but if I take a slope of that in a linear fit, it'll show me the rate at which the water heated up back to that temperature. Yep, it's a best fit regression. And so that's just like a really simple thing to do, but there are many, many things you can do. You can take integrals and derivatives and all kinds of stuff. And I think Jenny's going to show you something a little more complicated.
Well, once again, inspired by Joe. So let's see. I have to do just a little bit of switching out here.
That's a great activity to do with Newton's law of cooling.
Yeah.
And you take it out just to room temperature, it starts to go, and it has a nice curve fit.
Yeah. This is a really quick inquiry activity. Let's say you want the students to figure out, okay, what does acceleration do to gravity? Okay. We know that, or you can tell them that force equals mass times acceleration. And so given that equation and say, okay, figure out what acceleration due to gravity is. And you give them a couple of weights, and you give them this force sensor, and so, not you.
Sorry, it's going to go. It doesn't show up on screen.
Okay. So, but the thing is, if I put the spring on there, I have to zero it first. So Jenny's going to do that. And so a really quick thing would be, okay, I have 2 pounds on here. Obviously convert that to kilograms. And
I think it's 2 ounces.
oh, is it?
Yeah.
Yeah, 2 pounds would be a little bit heavy for that. Yeah. That would be mine. And so anyway, if I put this on the spring and don't let it bounce up and down, it'll give me a force reading. Okay? And so the students can record that force reading for that certain mass in kilograms. And if I take that out, I say, okay, well, I'm going to add some more mass to it. Okay? And so I add however many more kilograms I add and get a reading for that. And so after doing a few of these, they'll get an idea of how the force increases per amount of mass added, and then they can figure out the constant of acceleration in the formula.
Great. So actually, if you just keep it there, you can collect. So another nice way of these force vectors, these sensors, these probe can be really flexible. So you can even have students drag them on like wood, drag them on metal, and then see like, well, what are the different frictional forces, right? Have them start to experiment that way. Inspired once again by this sign. So we have it do that, right? You can say, well, why do I need to know any of that mathematics? When am I ever going to see that in my everyday life, right? Well, right here, right? So we've got an example of something that's damped harmonic motion, but that's got a period, that's got a frequency, right? And there are a lot of things that can be approximated by a mass on a spring. This is a huge thing, right? You can approximate almost everything. So these are the types of things that you can really get students to engage in scientific practices, right? They're collecting data from the real world and really being able to focus. Because all of the collection, granted, this is somewhat of a setup, but it's really not as hard as it seems. It kind of offloads the collection where students can then start to investigate, well, what is this graph? What does this mean? Just like Josh was saying. So we're going to do one more demo. Can I get a volunteer? Anybody want to volunteer? All right, yay! All right, you just have to come on up, yay! Okay, so that's...
Is it hard?
It's not hard.
Yes, and embarrassing.
All right, so what we've got here is a motion detector.
Oh,
so, and we're just gonna graph your motion. So you can go ahead and do whatever you would like to do. All right, you want to come back?
Oh, sorry.
Sorry, might have had a little bit of trouble there, but you can see that this is position. You can also look at velocity, so her velocity, and even acceleration. So what this is great for is getting students to just have an intuitive sense of, okay, well, this is where my position is, and you can get them to even do activities where they match graphs. And this is the fun part. So if you try to get a constant velocity, what do you think that might mean for you? What is that going to be? We can try. If you want to try a constant velocity.
I'm going to try a constant velocity, but then I'll end there and then. Oh, constant velocity. I can do this.
Yeah.
Oh yeah, very nice. All right. Watching very great. Yeah.
I can try walking the same speed.
Try walking the same speed. Yeah.
Okay. Yeah. Oh, you started cheering right over that.
I think we're actually out of the range.
Okay, now constant acceleration.
Actually, can you make a circle?
If I come back, it's still going to be velocity, so it's not going to be. I don't know what happens if I go and come.
Let's see. Try.
Wow,
There's
there's
an
fast.
experimental error there.
You probably have to start in minutes.
We can also
make a circle, yeah.
Well, you can't go back in time.
Yeah,
Exactly, you can't go back in time. And it's a way for kids to understand mathematical functions and why they have a value. You can't go back in time. So it's a different way of thinking about the vertical line. eye test and stuff like that.
And that's a great example of talking about experimental error, because clearly I didn't do that.
So you think.
Well, I am kind of.
How about a step function?
Oh yeah, you wanna try? We'll try one more.
Is
Does
it
anybody,
walking or what?
Is that gonna be?
You create a step function.
does anybody else wanna, I don't wanna put you on the spot, I'm sorry.
I can't figure out.
Does anybody wanna try to create a step function? All right, come on up.
Come on in. Yay for early volunteers.
We're the volunteers. We get extra cookies.
That's right.
Get extra calculators.
All right.
Wait a second.
No, I'm not still enough.
The time, it's a little bit, it also might be the time that I was.
But this is a good question for kids. How would you draw a step function?
Can I try?
Yeah, come on up. This was pretty darn good for the old sensor that we got.
That's
Let me
good.
just test that. I think one test for
What if you jump instead of?
All right.
Yeah, that's what I was wondering.
Really?
Oh, yeah.
You jump forward.
Okay.
Jump forward.
Oh. It's tricky.
Wow.
Very nice. So going in and out of the range of the actual probe.
Very creative.
It looks like you're doing a two-step there, Bob.
Really great. See,
I've had students line up like 3 or 4 in a row, and then they wait 2 seconds, one would jump out of the way,
oh, nice.
and then the other one would jump out of the way. It just gives them a different representation of what a step function is. And then they're also thinking about what does it mean, okay? For a certain period of the domain stays the same. You can get kids thinking about certain kinds of functions differently doing this. So you can do lots of math stuff with it as well.
Absolutely. So you can see how just by asking a few questions, you yourself can get really engaged. The students can get really engaged in asking their own questions and collecting their own data and conducting their own experiments just from that one motion sensor. So that was our very brief overview and demo. So oops, sorry.
Just one more thing. Maybe you're wondering, okay, how do I get materials for this? I'm not sure about the GoTen, but Vernier has a ton of probeware, and not only that, they have books and books of experiments that you can do, and they come with a CD that's editable labs. I exclusively use Vernier, not by choice. That's what the camera gave me, but.
But they are.
It was great. It was great.
But Vernier does, and this is all available on their website. They have videos on how to use it, how to set it up, and they've got free little bits of PDFs that you can download. And this is on the Vernier site.
You could also attach that to a graphing calculator and have it project the same thing.
Absolutely. Okay, so any questions?
Is there any way that we could use all 10 of the technologies in one lesson?
We're trying.
I see that. It's kind of fun how you're improvising jazz band stuff.
Well, you can see all the connections between it.
Yeah.
It's really the content, right? And there's different ways to teach the content. So.
And when you're like, I want to represent it this way, and this way, and this way, and math is in the science, and science can be illustrating the math.
Oh, yeah, because a lot of the scientific things have been measured and represented by numbers and graphs.
Absolutely.
So we'd like to give you at least 5 minutes to talk with your tables.
We were just talking, wondering if there's any possibility of using a camera on a Mac as some type of a motion sensor.
Absolutely.
Yes.
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 We'd be
Do
interested.
you want to say more about that? I'm like, yes.
Yeah, so a really good way to do this is, okay, let's say that you and I are throwing a football across the room. If we can get someone to film the whole frame, okay? If they step back far enough to film a whole frame with a Mac camera or a flip camera, whatever, what you do is you put a reference in the background. So you put a meter stick in the background, and you film the movie, you throw the football, whatever, and then when you upload it into Logger Pro, you tell Logger Pro that, okay, this length is 1 meter. And then you can plot data. I wish we could do this. It's kind of hard to explain like offhand like this, but you can track the football. So Logger Frame breaks down the video into frame per frame per frame. And so you can track the football as it goes across the frame. and that will be your data points over time. And so do the position over time, and when you take the first derivative, you get the velocity over time, and then you take the second derivative, you get acceleration of the football. So, I mean, that's a physics-based example that I can give you. You can also do things with, like, running. So like a human running, or a cat running, or like different animals running and their velocity and position over time, things like that. But, and how that's different in different animals. But, I don't know.
No, that's great.
I'm just saying something similar.
Yeah. Very similar to the GeoGebra or the Geometry Sketchpad example. You can upload and then also collect data.
Was that your question?
Yeah,
Yeah.
we're trying to figure out, so we have some cameras already built in, it's just
Yeah.
utilize them a little differently than.
One of the things you want to do is have reference points in it, so
Right.
if my students are doing something like that, I'll tell them, have something in the picture that you know the dimensions of, like an 8.5 by 11 piece of paper on the wall with something written on it, so you can use that as a reference point, and it just helps them with the measurement.
And I just want to say one last thing. You know, a lot of times it's wonderful to run. I love simulations, but students, as you know, in science and in math, have a real hard time connecting what they're learning in science to their everyday, like in the world around them. And so these are some really nice examples of how you can start to build that in your students and have them sort of appreciate. Oh, okay, yeah, I understand when I throw a football or when I slide across ice. They start to understand and think about the science behind it.